This video is about how we can calculate a change in K, or equilibrium constant, as temperature changes. So because reactions can absorb or release heat, changing temperature is the same as adding or removing a reactant or product. This means that the equilibrium constant will change as temperature changes, according to Le Chatelier's principle. For exothermic reactions, heat is a product. It's released. Therefore, K will decrease as T increases. As you increase T, you're adding product, which will suppress the forward reaction. For endothermic reactions, heat is a reactant. Therefore, K will increase as K increases. If heat is a reactant, adding reactants fuels that forward process, which increases K. This is the equation we use to calculate those changes. Let's break down the components one by one. ln is the natural log function. You should have this on your calculator. K1 and K2 are the equilibrium constants. R is our old friend, the gas constant, 8.314 joules per Kelvin. Delta H0 is the enthalpy of reaction, and we want this to be in joules specifically so that its units match the gas constant. T2 and T1 are the temperatures in question, and those temperatures need to be in Kelvin. You always need to match K1 with T1 and K2 with T2. So K1 is the equilibrium constant at temperature 1, and K2 is the equilibrium constant at temperature 2. Let's see this in action with a worked example. Let's consider this example problem. At 400 Kelvin, Kp equals 41, and the heat of reaction is minus 92.2 kilojoules. We want to know what is the value of Kp at 700 Kelvin. And this again is the Haber process for making ammonia. So let's make a table first of the various variables we have and figure out which ones we know, what those values are, and which one we don't know. So we've got K1 and K2. We've got T1 and T2. Note how I'm matching them. And we've got R, and we've got delta H. So our K1 will match with T1, so that's the one we've already been given. So we've got 400 Kelvin for our T1 matched up with 41 for our K1. Our T2 is that 700 Kelvin. And we don't know the K2. That's what we're going to try and solve for. R is always that ideal gas constant, 8.314 joules per Kelvin. Our delta H is negative 92.2 kilojoules, but we need to convert that to joules. So we're going to multiply by 1,000 to get negative 92,200 joules. So that's what we need to plug into this equation. So now all we need to do, plug everything in and crunch those numbers down. Let's do that. So natural log of K2 over 41 equals negative 92,200 over 8.314 times 1 over 700 minus 1 over 400. And we're going to pretend that those have decimal places on them for the sake of this problem. I'm going to work through this step by step. Feel free to pause here and then skip to the end to see if you've gotten the right answer. So natural log of K2 over 41 equals 11,100 times 1.42 times 10 to the minus third minus 2.50 times 10 to the minus third. So you note that our two negative signs canceled to give us a positive, and I just divided those out and put them in the same power of 10 to make the subtraction easier. You'll also note this is one of the few times where I don't solve an equation first. That's because we're going to have to deal with this natural log, and it's actually easier to do it this way. So natural log K2 over 41 equals 11,100 times negative 1.08 times 10 to the minus third. Natural log of K2 over 41 equals negative 12.0. So now we need to deal with the natural log. The way we do that is we raise both sides to the e power. So K2 over 41 equals e to the negative 12.0. If you crunch that, K2 over 41 equals 6.14 times 10 to the minus 6th. Now we multiply both sides by 41 to get our final answer. K2 equals 2.52 times 10 to the minus 4th. So take note, K2 is quite a lot smaller than K1. Our K1 was 41. And this makes sense because our reaction is exothermic. We would expect the K to decrease with increasing temperature. So there's our common sense check. So there you go, guys. Hope that made sense. If not, hit my office hours, send me an email, go to a pod, you know the drill.